Think about how often lenses shape your day, maybe often without you even noticing. From the glasses perched on your nose to the tiny camera lens capturing a moment on your phone, these transparent tools are just everywhere.
Yeah.
It makes you wonder what's the fundamental science behind how they bend light and create images.
Well, what's fascinating is that the same core principles govern all these applications, really. Whether it's the simple curve of a reading lens or, the really intricate design of a telescope objective,
Right.
it all comes down to how light interacts with these carefully shaped surfaces.
Exactly. And that's where we're diving deep into today. The fundamentals of lenses and that incredible ability they have to refract light, to bend it and form images. We've gathered a really comprehensive set of educational materials here, covering pretty much everything from the basic definition of a lens right through to detailed ray diagrams.
Yeah, that's good stuff.
Our goal is to give you a clear, insightful, and hopefully engaging understanding of this essential aspect of optics.
Absolutely. Our mission here is to unpack how these transparent pieces of material act like sophisticated tools, subtly shaping our view of the world. We want to go beyond just the definitions and help you really understand the why behind how lenses work.
Okay, so let's start right at the beginning then. What exactly is a lens?
Okay, so at its core, a lens is just a piece of transparent material designed specifically to refract light.
To bend it.
To bend it, exactly. What distinguishes it as a lens is that it's bounded by two curved surfaces, typically spherical ones.
Oh, right.
Though, interestingly, a flat surface can also be thought of as a spherical surface,
Yeah.
just with an infinitely large radius of curvature.
Huh. So it's the curvature that's the secret sauce, the key to bending light in a useful way.
Precisely. And the way those curves are shaped determines the type of lens and, critically, how it will affect a beam of light passing through it.
Right.
Our sources highlight two main categories: converging lenses, which you might also hear called convex lenses, and diverging lenses, also known as concave lenses.
Right. Let's kick off with converging lenses then. What are the key characteristics of a convex lens? What does it look like?
Okay, a convex lens is identifiable because it's thicker in the middle and it tapers towards the edges.
Right, bulges out.
It bulges out in the center, yeah. And this shape is crucial because when parallel light rays pass through a convex lens, they're bent inwards and brought together or converged at a focal point. Think of it like gathering the rays.
Okay, gathering them. And it's not just one uniform bulge, is it? I saw there are different types of convex lenses mentioned.
That's right. The material outlines three main types. First, you've got the biconvex lens. That's where both surfaces curve outwards.
Okay.
Then there's the plano-convex lens. One side is flat plano and the other is convex.
Flat on one side, curved on the other. Got it.
And lastly, we have the concavo-convex lens. Now, this one might sound a bit counterintuitive.
Yeah.
Because it has one concave inward curving surface and one convex outward curving surface. But the key here is that overall, it's still thicker in the middle than at the edges.
Ah.
And therefore, it still acts to converge light.
Okay, so the rule of thumb is thicker in the middle equals converging. Got it. Now, what about the other kind, the diverging lenses, the concave ones? How are they shaped?
Right, so a concave lens is pretty much the opposite shape. It's thinner in the middle and thicker out at the edges.
Ah, okay.
Instead of bulging outwards, it curves inwards at the center, like it's been scooped out a bit.
Right.
And as you might guess from the name diverging, when light rays strike a concave lens, they're bent outwards, they're diverged, as if spreading out from a point.
And just like with convex lenses, are there different forms of concave lenses too?
Yes, same idea. We have the biconcave lens where both surfaces curve inwards.
Okay.
The plano-concave lens, one flat surface, one concave surface.
Makes sense.
And then the convexo-concave lens. Similar to the concavo-convex case we just mentioned, this one has both a convex and a concave surface, but this time it's designed so it's thinner in the middle overall. And that thinness in the middle dictates its diverging effect. It's interesting, isn't it, how the overall geometry, not just the presence of curved surfaces, determines whether a lens converges or diverges light.
It really is. Now, here's something I found really cool in this source material. It mentions we can think of a lens as like a collection of tiny prisms. Can you explain that a bit more?
Absolutely, yeah. This is a really insightful way to visualize how lenses work. Imagine a convex lens, right? Think of it as being built from many tiny prisms stacked side by side.
Okay.
The prisms towards the top edge of the lens would have their flat bases pointing downwards, towards the center line. And the prisms near the bottom edge would have their bases pointing upwards, also towards the center.
And we know that when light passes through a prism, it always bends towards the thicker part, towards the base, right?
Exactly right. So when parallel light rays hit these different prism-like sections of the convex lens, each ray gets bent slightly towards the base of its own little local prism. Since the bases of the upper prisms point down and the lower ones point up, the net effect is that all the light rays get bent inwards towards the central axis of the lens, and that's what causes them to converge.
That makes so much sense.
Now, flip it for a concave lens. Visualize those prisms again, but this time their bases are pointing away from the central axis.
Okay, so outwards.
Outwards. The upper prisms would have bases pointing upwards and the lower ones downwards. So now when parallel light comes in, it gets bent outwards, away from the axis, causing the light to diverge.
That's a fantastic mental image. It really clarifies why convex lenses converge and concave ones diverge. What about the very center of the lens, though? The material says it acts like a rectangular glass slab.
That's a great point. Right in the very middle of the lens, the two surfaces are almost parallel to each other, especially for a thin lens. So light passing right through this central region, assuming it hits perpendicularly, doesn't undergo significant bending or deviation. It might experience a tiny sideways shift, especially in thicker lenses, but its direction remains largely unchanged.
Like going through a window pane.
Pretty much, yeah, like passing through a regular flat piece of glass.
Okay, so we've got the different types of lenses and this really helpful prism analogy. Now, the material introduces some technical terms we really need to get our heads around. Let's start with center of curvature. What's that?
Right. So because the surfaces of a lens are usually parts of spheres, each surface is essentially a segment of some larger imaginary sphere. The center of curvature for a particular lens surface is simply the center of that imaginary sphere it was cut from.
Okay.
And since a lens generally has two surfaces, it will have two centers of curvature. We usually label them C and C.
And the radius of curvature, then, is just the radius of those imaginary spheres.
Precisely. It's the distance from any point on that spherical lens surface back to its center of curvature. So R and R.
Right.
For a thin lens, we often approximate this distance as being measured from the very center of the lens itself, the optical center we'll get to in a sec. And importantly, if a lens is equiconvex or equiconcave, meaning both its surfaces have the same amount of curve, then the radii of curvature for both surfaces will be equal. R equals R.
Got it. Okay. What about the principal axis? That sounds like a key reference line.
It is. The principal axis is fundamental. It's simply the imaginary straight line that passes right through both centers of curvature, CS and CF.
Okay.
It acts as the central line of symmetry for the whole lens system. Think of it like the main highway through the lens.
And then there's the optical center. What's special about that point? O.
The optical center, yeah, usually marked O, is a very specific point located right on the principal axis, usually within the lens itself. Its defining property is that any ray of light that passes exactly through the optical center emerges from the lens traveling in the same direction it entered.
So no bending at that point.
Well, for thin lenses, we pretty much consider to pass straight through, undeviated, no shift. For thicker lenses, technically there's a slight sideways displacement, a lateral shift, but the crucial thing is the outgoing ray is still parallel to the incoming ray. So yeah, you can think of it as the no bending direction point within the lens.
Now we're getting to the principal foci. This seems a bit more involved as there's a first one and a second one mentioned. Let's tackle the first focal point, FS, first. What's that about?
Okay, FS. For a convex lens, the first focal point is a specific spot on the principal axis. If you place a point light source at FS, the rays spreading out from it will, after passing through the convex lens, emerge as a beam of light perfectly parallel to the principal axis.
So it's the starting point to get parallel light out.
Exactly. Think of it as the point you put a tiny bulb if you want to create a searchlight beam. Now, for a concave lens, FS is defined a bit differently. It's the point on the principal axis towards which incoming rays must appear to be converging.
Appear to be?
Yeah, so imagine rays heading towards that point, FS, before they hit the lens. After passing through the concave lens, those rays will emerge parallel to the principal axis.
Okay, slightly different definitions, but both relate to getting parallel light out of the lens. So what about the second focal point?
Right, F-Uris. This is probably what most people think of when they just hear the word focus. For a convex lens, if you have parallel rays of light coming into the lens, parallel to the principal axis, they will all converge. They'll meet, after refraction, at the second focal point, F.
That's the burning glass point.
That's the burning glass point, precisely, where you feel the heat from focused sunlight. For a concave lens, if parallel rays come in, they bend outwards, they diverge. But if you trace those diverging rays backwards, they will appear to originate from the second focal point, F.
Ah, so it's a virtual point for concave lenses.
Exactly. It's on the same side of the lens as the incoming parallel light. The rays don't actually cross there.
And is there a relationship between the distances of these focal points from the optical center?
The focal length.
Yes, absolutely. The distance from the optical center to the first focal point, F0, is called the first focal length, F.
And the distance from O to the second focal point, F, is the second focal length, F0.
Mm.
Now, if the medium on both sides of the lens is the same, like air on both sides, which is usual,
Yeah.
then these two focal lengths are numerically equal. So FO, it's F0.
Yeah.
And when people just talk about the focal length of a lens, usually denoted by just F, they almost always mean the second focal length, FO.
The material also makes a point about a convex lens having a real focus and a concave lens having a virtual focus. What's the practical difference there? Why does that matter?
Good question. The distinction is about whether the light rays actually converge at that focus point or just appear to diverge from it.
Right.
In a convex lens, the parallel rays physically meet up at F0. It's a real focus. Go put a screen there, like a piece of paper, and you'd see a bright, focused spot of light. You could project an image there.
Yeah.
In a concave lens, the parallel rays bend outwards. They never actually cross at F on the other side. They only appear to be coming from that point F's on the same side as the incoming light if you trace their paths backward.
Yeah.
So it's a virtual focus. You couldn't put a screen there and see a focused spot directly from those parallel rays.
I see. That virtual concept is important. Now, what happens if we have oblique parallel beams of light hitting the lens? So parallel rays, but coming in at an angle not parallel to the principal axis. Do they still focus at F?
Ah, good point. Not necessarily at F itself, no. If a parallel beam of light hits the lens at an angle to the principal axis obliquely, it will still be brought to a focus for a convex lens, or appear to diverge from a point for a concave lens.
Okay, where?
That point will lie within what's called the second focal plane. This is an imaginary flat plane that is perpendicular to the principal axis and passes right through the second focal point, F.
Yeah.
So think of sunlight hitting a window at an angle. Different parts of that angle beam will focus at slightly different points, but all those points will be located somewhere on that focal plane. The exact spot depends on the incoming angle.
And finally, we have the focal plane itself. So that's just a plane perpendicular to the principal axis passing through either FAL or FEO?
Exactly. We have a first focal plane through F there and a second focal plane through FEO. As we just discussed, they're crucial for figuring out where off-axis parallel rays will end up.
Okay, that was a lot of technical terms, but I think we have a much clearer picture now. Let's move on to how these lenses actually, do the refracting. The materials specifically mention equiconvex and equiconcave lenses. Is the refraction fundamentally different for them?
The basic physics, the fundamental law of refraction, Snell's law, which describes how light bends when it goes from one medium to another, like air to glass, is the same for all lenses. In an equiconvex lens, light coming from air into the glass bends towards the normal. That's an imaginary line perpendicular to the surface right where the light hits. Then, when it exits the glass back into the air at the second surface, it bends away from the normal for that surface. But because of the overall outward curve of the equiconvex lens, the net effect of these two bends is that the light is directed inwards towards the center. It converges.
And for an equiconcave lens, the bending happens in the opposite overall direction.
Correct. Light still bends towards the normal entering and away from the normal exiting. But the inward curvature, the shape of the equiconcave lens, means that the overall effect is the light rays bend outwards, away from the central axis, so divergence.
Right.
The key takeaway is really that the geometry of the lens surfaces dictates the overall convergence or divergence. Of course, the material matters too. A higher refractive index bends light more, leading to a shorter focal length and a stronger lens effect.
Now, when we draw these ray diagrams to visualize where images form, the source material mentions a thin lens approximation. We show the bending happening at like a single vertical line through the optical center. Why do we simplify it like that?
Yeah, that's a really practical simplification. It just makes drawing the diagrams much, much easier without losing too much accuracy, at least for most lenses that are genuinely thin.
Right.
In reality, as we just said, the bending, the refraction happens at both surfaces of the lens.
Yeah.
But if the lens's thickness is pretty small compared to its radii of curvature, and also compared to how far away the object and image are, then we can approximate the total bending as if it all happened at a single plane right down the middle at the optical center.
Okay.
It doesn't usually change the predicted position or size or nature of the image very much,
Yeah.
and it saves us the hassle of calculating the bend at two separate surfaces.
Are there situations where this approximation breaks down?
Oh, definitely. For very thick lenses, like, really chunky ones, or in high-precision optical systems like microscopes or telescopes, engineers can't use the thin lens approximation. They have to trace the rays through both surfaces accurately. But for understanding the basics, it's a great tool.
Makes sense for simplifying things. Now, let's talk about the principal rays. These are the specific rays we use to actually construct those diagrams. There are 3 main ones mentioned. Can we go through each one for both convex and concave lenses?
Sure. The first principal ray is probably the easiest one to remember. Any ray of light that travels directly through the optical center of the lens just continues in a straight line, undeviated.
No bending at all.
Well, for a thin lens, effectively no bending, no deviation. As we said, technically a slight shift in thick lenses, but the direction is unchanged. And this holds true for both convex and concave lenses. Straight through the middle.
Okay, straight through the middle, easy enough. What's the second principal ray?
The second one involves parallel light. It's a ray that starts off traveling parallel to the principal axis before it hits the lens.
Okay.
For a convex lens, after it refracts, this ray will pass right through the second focal point, F here, on the other side of the lens.
Right, converging towards F.
Exactly.
Yeah.
Now, for a concave lens, a ray coming in parallel to the principal axis will refract outwards, diverging. But if you trace that diverging ray backwards, it will appear to have come from the second focal point, F, on the same side of the lens the light came from.
Okay, so convex goes through F on the far side. Concave appears to come from F on the near side.
Got it.
What's the third principal ray?
The third one is sort of the reverse of the second one, in a way. It involves the first focal point, F here.
Oh, okay.
For a convex lens, if you have a ray that passes through the first focal point, F here, on its way to the lens, then after it refracts to the lens, it will emerge traveling perfectly parallel to the principal axis.
So F here acts like the launch point to create parallel light.
Precisely. Now, for a concave lens, it's a ray that is initially directed towards the first focal point, F here, which is on the far side of the lens.
Oh.
If that ray continued, it would hit F here. But of course, it hits the lens first. After refracting through the concave lens, this ray will also emerge parallel to the principal axis.
Interesting. So both types of lenses have a way to turn light associated with F here into parallel light.
That's right. It's a key property used in things like collimators, instruments designed to produce parallel beams.
So to figure out where an image is formed by a lens, we just need to draw, say, any 2 of these 3 principal rays coming from a point on the object, like the top of an arrow,
Yep.
and see where those 2 rays intersect after they've gone through the lens.
Exactly. That point where the refracted rays actually cross is where the image of that point on the object will be formed. That gives you a real image.
And if they don't cross, if they're diverging?
Good point. If the refracted rays are spreading out, like after passing through a concave lens or a convex lens when the object is too close, then you trace those diverging rays backwards using dashed lines. The point where those dashed lines appear to meet is the location of the virtual image.
Okay.
By doing this for maybe the top and bottom points of the object, you can determine the image's location, its size, and its nature, whether it's real or virtual, and whether it's upright, erect, or upside down, inverted.
Perfect. Let's actually dive into that image formation now, starting with convex lenses. The materials describe different scenarios based on where the object is placed relative to F here. What happens when the object is way out there, at infinity?
Right. When an object is extremely far away, like a distant star or even just a building across town, the light rays reaching the lens from any point on that object are essentially parallel to each other.
Okay.
And if they're also parallel to the principal axis, a convex lens will, as we know, converge these parallel rays at its second focal point,
Correct.
F here. The image formed there is real. You could put a screen there and see it.
Huh.
It's inverted, although orientation is a bit fuzzy for infinitely distant things. And it's extremely small, highly diminished, practically a point focus.
Like the burning glass again?
Exactly like the burning glass concentrating sunlight. Or is how a camera lens forms an image of a distant landscape onto the sensor, which is placed right near the focal plane.
What if we bring the object closer, but still keep it beyond twice the focal length, so outside 2F euro?
Okay, object distance greater than 2F euro. In this case, the convex lens forms an image between f euros and 2f euros on the other side.
Ah, closer to the lens than to a euro.
Yep. This image will still be real, it'll still be inverted, but now it's diminished smaller than the object, but not just a point anymore.
Okay.
This is a common setup for cameras taking pictures of, say, people or objects that aren't miles away. You get a smaller, real image on the sensor.
Now, what happens at that specific point when the object is placed exactly at 2f euro?
Ah, the magic point. If the object is precisely at a distance 2f euros in front of a convex lens, the image forms exactly at 2f euros on the other side.
Right.
The image is still real, still inverted, but crucially, it's exactly the same size as the object. Magnification is 1, or rather -1, because it's inverted.
Interesting. Any uses for that?
Yeah, sometimes in photocopiers or in certain telescopes like terrestrial telescopes where you might want to re-invert an image without changing its size.
Okay, moving the object even closer now. So it's between the first focal point and 2f euros. What kind of image do we get then?
Right, object between f euro and 2f euro. Now the image forms beyond 2f euro on the other side. So it's further away from the lens now.
Okay.
The image is still real, still inverted, but now it becomes it's larger than the original object.
Ah, so this is how projectors work.
Exactly. This is the principle behind cinema projectors or slide projectors. You place the small slide or film just outside the focal point, and the lens projects a large, magnified real image onto the distant screen.
What happens if we push the object even closer and place it right at the first focal point, f?
Object at f. Remember what f does. Rays from f emerge parallel after the lens.
Ah, right. Parallel rays.
So if you place the object at fs, the refracted rays emerge parallel. Parallel rays, technically, meet at infinity. So we say the image is formed at infinity.
Wow.
It's considered real, inverted, and highly magnified, essentially infinitely large. This setup is used in devices like collimators, often found in spectroscopes, to take light from a source at the focus and create a parallel beam for analysis.
And finally, the case everyone knows. What if we place the object even closer, between the lens and fs? This is the magnifying glass scenario, right?
Exactly. This is the magic behind the magnifying glass. When the object is placed within the focal length between the optical center O and the first focal point fs, the rays coming out of the convex lens actually diverge. They spread out.
So no real image.
No real image formed on the other side? No. But if you, the observer, look back through the lens from the other side, your eye traces those diverging rays backwards. And they appear to originate from a point behind the object, on the same side of the lens as the object. This is a virtual image.
And what's it like?
It's erect, upright, the same way up as the object, and it's magnified. It looks bigger than the object really is. That's your magnifying glass or simple microscope effect right there.
Fantastic. So it seems like convex lenses are incredibly versatile. Real images, virtual images, magnified, diminished, same size. It all depends on where you put the object.
That's the key takeaway.
What are the overall trends then as we move an object closer and closer towards a convex lens?
Okay, think about it. As the object moves from infinity towards the lens, the image starts at f and moves away from the lens, out past 2f euro, and eventually towards infinity as the object reaches f.
Right, the image moves further out.
And the size. It starts highly diminished at f, gets smaller, but still diminished beyond 2f euro, becomes the same size at 2f euro, then gets magnified between 2f euro and f euro.
Okay, size generally increases.
And the nature. It's real and inverted all the way from infinity up to f. Then, the instant the object crosses inside f, bam, it flips to being virtual and erect.
That's a really helpful summary for convex lenses. Great. Now let's switch gears completely and look at concave lenses. How do they form images? Are they as complicated?
Actually, no. Concave lenses are much more predictable, you could say. They're simpler in terms of the images they form.
Okay.
Let's take the extreme case first. Object at infinity, parallel rays come in. What does a concave lens do?
It diverges them, makes them spread out.
Right, and where do they appear to diverge from?
From the second focal point, F, on the same side the light came from.
Exactly. So for an object at infinity, a concave lens forms an image at F. It's virtual because the rays don't actually cross there. It's erect, though again, orientation for infinity is tricky, and it's highly diminished, basically a point.
Okay. And what happens if we bring the object closer to any finite distance from the concave lens anywhere else?
This is the simple part. No matter where you place an object in front of a concave lens, anywhere between infinity and right up against the lens, the image formed will always be virtual. It will always be erect, upright, and it will always be diminished, smaller than the object.
Always, no exceptions.
No exceptions. Always virtual, always erect, always diminished.
Where does the image form?
It'll always be located between the optical center O and the second focal point, F Eurus, and always on the same side of the lens as the object.
So a virtual focus, like F euro for a concave lens, isn't a place where light actually converges. Does that mean you can't, like, project that image onto a screen?
That's exactly right. You can't project a virtual image onto a screen or piece of paper. You can only see it by looking through the lens. Your eye does the work of tracing the diverging rays back to the virtual image location.
So just to be absolutely clear, no matter where you put the object with a concave lens, you always get a virtual, upright, smaller image, somewhere between the lens and its focus on the object's side.
Precisely. As you move the object closer to the concave lens, that virtual image also moves a bit closer to the lens, starting from F Eurus and moving towards O. And it does get slightly larger as the object moves closer, but importantly, it always remains smaller than the object itself.
Wow, that's a huge contrast to the convex lens. So just to quickly recap the key differences between the images they form.
Okay, main differences. Convex lenses can do it all. Real or virtual images, magnified, diminished, or same size. Inverted or erect. It all depends on the object position relative to F Eurus.
Right.
Concave lenses. Always the same outcome, qualitatively. Always virtual, always erect, always diminished, regardless of object position.
Much simpler. Okay, now that we have a good handle on how the images are formed, let's talk about something really crucial for calculations. The sign convention. This seems absolutely vital for getting the formulas right.
Oh, it is. You absolutely have to use a consistent sign convention, otherwise the maths just won't work out. It's like agreeing on which way is north before giving directions.
Makes sense. So what's the standard convention?
Okay, standard approach. First, the optical center of the lens is your origin, your 0, point on the graph, basically.
Okay.
Second, we usually place the object on the left side of the lens, and we assume light travels from left to right. That direction, left to right, is taken as the positive direction for measuring distances along the principal axis.
So anything to the right of O is positive distance, anything to the left is negative distance?
Exactly. Distance is measured from O in the same direction as the incident light, usually rightwards, are positive. Distances measured from O in the opposite direction to the incident light, usually leftwards, are negative.
Okay, so the object distance, U, which is measured from O to the object on the left, that's always negative then?
Almost always, yes. Since the object is conventionally placed to the left, U is typically negative.
And what about heights, above and below the axis?
Simple rule there. Heights measured upwards from the principal axis are positive. Heights measured downwards are negative. So an upright object has a positive height, an inverted image has a negative height.
Okay, distances left, right, heights up, down. Now, how does this apply specifically to focal length, F, and image distance, V, for our two lens types?
Right. By convention, based on how they've gunned light. A convex lens, which converges light toward the right positive direction, is assigned a positive focal length, plus F.
Okay, convex is positive.
A concave lens, which diverges light, making it appear to come from the left, negative direction, is assigned a negative focal length, F.
Concave is negative F.
Got it. What about the image distance, V?
That depends on where the image forms. If the image is formed on the right side of the lens, where the light actually goes after refraction, it's a real image, and its distance V is positive.
Real image, positive V.
If the image is formed on the left side of the lens, where the light only appears to come from, it's a virtual image, and its distance V is negative.
Virtual image, negative V. And think about concave lenses. They always form a virtual image on the left side. So for a concave lens, V will always be negative. And also, since the image is always between O and F, the magnitude of V will always be less than the magnitude of UVU.
Ah, okay. So for concave, U is negative, F is negative, and V is always negative and smaller in magnitude than U.
You've got it. That consistency is key.
All right, with the sign convention hopefully clear now, we can introduce the famous lens formula. What is this formula, and what do the terms represent again?
The lens formula is the workhorse equation here. It connects the object distance, U, the image distance, V, and the focal length, F, of a thin lens. It's written as 1 over V minus 1 over U equals 1 over F. So 1V, 1U equals 1F.
1V, 1U is 1F. Okay.
This formula works beautifully for both convex plus F and concave MAF lenses, but only if you religiously plug in the values for U, V, and F using the correct signs we just discussed.
Right, the signs are everything.
They are. It allows you to calculate any one of those three distances if you know the other two. It's derived using geometry and Snell's law at the lens surfaces, but we don't need the derivation today.
Okay, good. The materials say the derivation is outside our scope for this deep dive.
Correct. The crucial skill is knowing the formula and applying the sign convention correctly when you put the numbers in.
Now, another key concept when we talk about images is linear magnification. What does that tell us? How much bigger or smaller the image is?
Exactly. Linear magnification, usually given the symbol m, is simply the ratio of the height or size of the image, let's call it I or h, to the height of the object, O or h. So m equals I.
Okay, image size over object size.
Yep. And conveniently, it turns out this ratio is also equal to the ratio of the image distance, v, to the object distance, u. So m equals v.
Ah, m equals v. That's useful if we know the distances.
Very useful. Again, you must use the correct signs for v and u when calculating m this way.
And the sign of the magnification, m itself, also tells us something important, right? About whether the image is upright or inverted.
Absolutely critical point. The sign of m tells you the orientation. If m is positive, the image is virtual and erect, upright.
Positive m means virtual and erect.
If m is negative, the image is real and inverted, upside down.
Negative m means real and inverted. Okay.
And the number itself, the magnitude of m, ignoring the sign, that tells you the size change. If the absolute value m is greater than 1, the image is magnified, bigger. If m whole 1 is the same size, if m1 is diminished, smaller.
Okay. So for a convex lens, m could be positive or negative and bigger, smaller, or equal to 1.
Yep. Convex lenses run the whole gamut, depending on where u is. But for a concave lens, what do we know about its images?
Always virtual, erect, and diminished.
Right. So for a concave lens, it must always be
positive because it's erect and less than 1 because it's diminished.
Exactly. Because m and for concave, both v and u are negative, so vu is positive.
Yeah.
And since vu, the value is less than 1. It all fits together.
Nice. Okay, let's move on to the power of a lens. What property does that describe? Is it like how strong the lens is?
That's a great way to think about it, yeah. The power of a lens is basically a measure of how strongly it bends light rays, how it converges or diverges them.
Okay.
A lens with a short focal length bends light a lot. It's got high power. A lens with a long focal length only bends light gently, and those got low power.
So shorter focal length, more power.
Exactly. Think of a really curved fat lens, short focal length, high power, a thinner, flatter lens, longer focal length, lower power. It quantifies that bending ability. A higher power means a bigger change in the light's direction.
And how is this power actually measured? What's the unit?
The power P of a lens is defined simply as the reciprocal of its focal length, F. So P equals 1F. But, and this is crucial, the focal length must be expressed in meters for this calculation.
Meters, not centimeters or millimeters.
It must be meters. If you use meters for F, then the unit for power P comes out in diopters, abbreviated as D.
Edges. Okay, I've seen that on my glasses prescription.
Exactly. So a lens with a focal length of exactly 1 meter has a power of 11 equals 1 dioptra. A lens with f, 0.5 meters, has P equals 10.5 equals 2 diopters.
And do convex and concave lenses have different signs for their power, just like their focal length?
Yes, it follows directly. Since a convex lens has a positive focal length, f, its power, P equals 1 plus f, is also positive. Positive power means converging.
Right.
And since a concave lens has a negative focal length, f, its power, P equals 1f, is negative. Negative power means diverging.
So my glasses prescription, if it's a minus number, means I have concave lenses for nearsightedness.
That's generally right, yes. For example, convex lens with f plus 20 centimeters is plus 0.2 liters has a power P equals 10.2 plus 5.0 D. A concave lens with f equals 25 centimeters has P 1 minus is split on 0.25 equals needs 4.0 D.
Okay. What happens if you stick multiple thin lenses together, like right in contact? How do their powers combine?
For thin lenses in close contact, it's actually quite simple. The power of the combination is just the algebraic sum, meaning you add them up, paying attention to the plus or minus signs of the powers of the individual lenses.
Oh, just add the dioptry.
Pretty much. So total ears plus Piro plus Piros plus Piers and so on. If you put a plus 2.0 D lens right next to a negative 1.5 D lens, the combination acts like a single lens with a power of plus 2.0 plus minus 1.5 plus 0.5 D.
Handy. Okay, now let's connect all this theory to some real-world applications of lenses. The magnifying glass, or simple microscope, is probably the most common one people encounter. How does it work based on what we've discussed?
Right, the magnifying glass. It's simply a convex lens, usually one with a fairly short focal length.
Okay, convex, short f.
And it works based on that last case we discussed for convex lenses. When you place the object within its focal length, so object distance u is less than f.
The virtual image case.
Exactly. When the object is between O and f, the convex lens produces a virtual, erect, and magnified image located on the same side of the lens as the object.
So how does that help us see small things?
Well, normally, to see something clearly, your eye needs to focus. And there's a limit to how close you can bring an object and still keep it in focus. That's called the least distance of distinct vision, usually about 25 centimeters or 10 inches for a typical adult eye. Let's call it D.
Okay, D equals 25 centimeters.
If you try to bring tiny print closer than D, it just gets blurry. But with a magnifying glass, you can place the object much closer to your eye, well inside D, specifically inside the lens focal length f. The lens then takes that nearby object and creates a magnified virtual image that appears to be much farther away, typically at or beyond D, 25 centimeters.
So the lens forms a large virtual image far enough away for our eye to focus on comfortably.
Precisely. You get the benefit of bringing the object physically close, which makes it appear larger anyway, plus the angular magnification provided by the lens creating that virtual image. It makes the details subtend a larger angle as your eye.
And is there a formula for how much magnification you get?
Yes, the magnifying power M for a simple microscope, when the final virtual image is formed at the least distance of distinct vision, D, is given by the formula M equals 1 plus DF.
M1 plus DF.
Where D is that near point distance, usually 25 centimeters, and F is the focal length of the convex lens, also usually in centimeters for this formula.
So a shorter focal length, F, gives a bigger magnification, M.
That's right. A lens with F of 5 centimeters would give M plus 252.5 equals 1 plus 5 equals 6 times magnification. A lens with F 2.5 centimeters would give M plus 252.5 equals 1 plus 10 equals 11 times magnification.
But you can't just make F infinitely small, right?
No, there are practical limits. Very short focal length lenses tend to be very curved, thick, and suffer more from aberrations, image distortions, and they also give you a very small field of view. So there's a trade-off.
What are some common uses for these magnifying glasses?
Oh, loads. Reading small print, obviously. Examining stamps or coins. Detailed work like watchmaking or jewelry repair where you need to see tiny components. And they're often built into scientific instruments, like a small reading lens to help read the fine marks on a vernier scale.
Makes sense. Now, the materials also list several other really important applications of lenses. Can you give us a quick tour of some key ones and how the principles fit?
Sure. Well, we've touched on some already. Convex lenses are the heart of objective lenses in refracting telescopes, cameras, and those slide-to-cinema projectors we mentioned. In all those cases, the convex lens forms a real, usually inverted image of an object, distant for telescopes, cameras, nearby for projectors.
Okay, what about eyes and glasses?
Right. Our own eye lens is a convex lens. It forms a real inverted image on our retina. Spectacles use lenses to correct vision problems. For long-sightedness, hypermetropia, where the eye doesn't focus strongly enough and the image would form behind the retina, you use a convex lens in the glasses. It gives the light an extra bit of convergence before it even enters the eye, helping the eye lens focus it correctly on the retina.
And for short-sightedness, myopia.
That's where the eye focuses too strongly and the image forms in front of the retina. So you need the opposite effect. You use a concave lens in the glasses.
The diverging lens.
Yep. It diverges the incoming light slightly, pushing the focal point back just enough so the eye lens can then place it perfectly on the retina.
Clever. And bifocals.
They just combine both.
Yeah.
Usually a convex section at the bottom for reading, near vision, and a differently powered section, maybe concave, maybe less convex, maybe flat, at the top for distance vision.
We already covered magnifying glasses, convex. What else?
Well, spectroscope collimators use a convex lens to take light from a slit placed at FEO and produce a parallel beam, which is needed for prism or grating analysis.
Right, object at FEO gives parallel rays.
Interestingly, some telescopes, like the Galilean telescope, actually use a concave lens as the eyepiece lens, working with a convex objective, to produce a final image that's upright. And a really important application is using combinations of convex and concave lenses, often made of different types of glass.
Why combine them?
To reduce chromatic aberration. That's the annoying color fringing you sometimes see, because a simple lens acts like a prism and splits white light slightly, focusing different colors like red and blue at slightly different points. Combining lenses carefully can counteract this.
Fascinating. Okay, one last area the material touches on. The experimental determination of focal length. How would you actually measure the focal length of, say, a convex lens in a lab?
There are a couple of fairly standard methods. The quickest, roughest way is the distant object method.
How does that work?
You take your convex lens and you use it to form an image of a very distant object like a tree or building far outside the window onto a screen, like a piece of card. Since the rays from a very distant object are almost perfectly parallel when they reach the lens, The lens will focus them very close to its second focal point, F. So you just move the screen back and forth until you get the sharpest possible image of the distant object.
And the distance.
The distance between the lens and the screen where the sharp image forms is then a pretty good approximation of the focal length.
Wow. Simple. Does it work well?
It's good for a quick estimate, but infinity isn't truly infinity, so it's usually slightly off. A more accurate method often used in school labs is the auxiliary plane mirror method.
Okay. Sounds more complicated. How does that work?
There are a couple of ways to set it up. One way, you place the convex lens directly on top of a flat plane mirror lying on the table.
Lens on mirror. Okay.
Then you hold a pin, like an optical pin, vertically above the lens on its principal axis. You look down from above the pin, you'll see the pin, and you'll also see its inverted image formed by the lens-mirror combination.
Right.
You adjust the height of the pin up and down until there's no parallax between the tip of the actual pin and the tip of its inverted image. That means they are exactly at the same location in space.
No parallax means they're at the same spot. Why does that happen?
It happens when the pin is placed exactly at the first focal point of the lens. Rays from the pin at F euros travel down, become parallel after passing through the lens, hit the mirror perpendicularly, reflect straight back up along the same path, go back through the lens, and reconverge to form a real inverted image right back where the object pin is at F euro.
Ah, so the no parallax position is the focal point.
Exactly. So the distance from the pin tip down to the optical center of the lens, approximated as the middle of the lens or average from the top surface, is equal to the focal length, F.
That's clever, using the mirror to send the light straight back.
It is. You can also do it on an optical bench with the pin, lens, and mirror on separate stands, adjusting the pin position until its image, formed after going through the lens, reflecting and coming back through, coincides with itself. Same principle.
Brilliant. Okay, wow, we have covered a huge amount of ground today, from the absolute basics, what is a lens, all the way through the different types, convex and concave, how they bend light using refraction.
That prism analogy, all those technical terms like focal points and principal axis.
How the images change completely depending on where the object is for a convex lens, but stay consistent for a concave lens.
The absolutely crucial sign convention, the lens formula, magnification, lens power in dioptries.
And wrapping up with real-world applications like magnifying glasses, spectacles, and even how to measure focal length experimentally.
It really is remarkable, isn't it, how these seemingly simple pieces of shaped glass or plastic are just so fundamental to how we see and interact with the world, underpinning everything from our own eyes to, the most advanced telescopes looking out into the universe.
Absolutely. So thinking about all that, about how both convex and concave lenses manipulate light in their own ways, here's a final thought for you, our listener, to ponder. Can you imagine scenarios where combining these lenses, maybe multiple convex and concave elements together in really intricate ways, could unlock even more sophisticated optical effects, going way beyond just simple vision correction or reducing basic aberrations like chromatic aberrations?
That's a great question to leave things on. Think about the complexity inside a modern zoom lens for a camera, or the optics inside a high-power microscope or a space telescope. The way designers combine multiple lens elements, carefully choosing shapes, materials, and spacing. It allows for incredible control over light, enabling things like massive magnification ranges, ultra-high resolution, correction for multiple complex aberrations simultaneously, even image stabilization. It all builds on these fundamental principles we've explored today, but taken to an extraordinary level of refinement.
It certainly gives you a new appreciation for that camera lens or even just your glasses. Well, thank you for taking this deep dive with us into the really captivating world of lenses. We hope this exploration has provided you with a clearer and perhaps more insightful perspective on this essential piece of optics.